DeepVisus, systems that build themselves, based on Chapter 5 of George Kampis's Self-Modifying Systems in Biology and Cognitive Science, 1991. If classical systems follow fixed rules within rigid boundaries, can we imagine systems that don't just follow rules, but write their own as they go? Welcome back to DeepVisus. In our last episode, we reached the philosophical threshold. Chapters 3 and 4 showed us the limits of the mechanistic universe, where systems are trapped inside the logic they were born with. Today, in Chapter 5, George Kampis begins to chart a way out. He offers not just a new kind of model, but a new kind of system altogether. One that can grow, reorganize, and invent itself. Let's explore the emergence of what he calls the self-modifying system. Chapter 5. Component Systems Beyond Algorithmic Dynamics. We begin with the problem. Nearly every model in science, from physics to computation, is built on the assumption that the rules are fixed. The number of variables, the way those variables interact, even the equations themselves, these are all hard-coded from the start. But what if the most important feature of living systems is precisely that they don't play by fixed rules? Enter the self-modifying system. Kampis introduces a class of systems that do not keep their structure constant. Instead, they are made of components that can interact dynamically, create new components, modify their own architecture. And that leads us to the core definition. A self-modifying system is a system whose internal dynamics can lead to the creation of new components or interactions that permanently modify the system's own structure. In other words, it can change the rules of its own evolution. It can increase the dimensionality of its state space. It can transform what counts as a system variable. This is more than reconfiguration. It's genuine, open-ended construction. Why this is a break from algorithmic thinking. Traditional systems are state-determined. They evolve within a predefined space, following rules set in stone. But in component systems, the system's own activity can add new types of behavior, expand its own state space, introduce irreversible structural novelty. This is non-Turing behavior. It's not just hard to simulate, it's formally outside the scope of computable dynamics. Kampis is telling us that living systems do something no machine can. They produce their own variables, their own modes of interpretation, their own contexts. A living model of life. He grounds this not in metaphor, but in macromolecular biology. Think about it. A cell produces enzymes that change what it can metabolize. The genome is not a read-only tape. It's part of a feedback-rich construction process. The components, proteins, genes, membranes, are built by the system, for the system, within the system. This is the essence of a self-modifying component system. Not an algorithm, but a construction process embedded in the world it alters. Why it matters for cognition and biology. Kampis believes this is the only kind of model that can truly capture evolutionary creativity, developmental emergence, mental innovation. If the system can't rewrite itself, it can't really model life. So Chapter 5 isn't just a new chapter. It's the unveiling of a new framework. One that says, maybe the most truthful models are not the ones that simulate life, but the ones that act like life. Kampis has now cleared the ground and laid the first bricks. He's ready to build something that builds itself. In our next episode, we follow this idea into motion. In the following episode, we'll explore how systems can generate more than they started with, and why that changes everything about what it means to understand biology, mind, and information. Until then, stay sharp, stay curious, and remember, sometimes the most revolutionary system builds itself while you're watching. DeepVisus, where vision meets depth.